These are my notes on Biostat, starting with ARR, which equals to control minus treatment, and rate of treatment is equal to number of infections divided by the population. Okay. So all of this is basically from the page of step 1 Biostat, where they give you all the formulas. I would recommend that you either watch the video that I made from step 1, I added it to the step 2 playlist, or just give it a look over so that you understand what's going on. So absolute risk reduction, it's basically you take the risk in control group and you subtract the risk in treatment group, and whatever is left over is the amount that the risk basically controlled. Reduced. It's absolute risk reduction. The rate of treatment is equal to number of infections over the number of people, or whatever it is. This one, I don't think it comes in handy. It's this one that you need to know. If they give you that 90% of the people in control group got it, and then 60% of people in the treatment group got it, that means 90 subtract 60 and 30%, so it reduced 30%. Right. You see a square in the question, for example, like this, it's chi-squared, okay, or chi-squared, however you say it. If p-value is more than significance level of alpha, there is no significant difference in group means. Data do not provide statistical evidence that HA is true. Right. So if p-value is more than, so say alpha is 0.03 and p-value is 0.05, normally we would consider 0.05 as a significant as a value of significance, right? Because it's below 0.05 or below, right? However, if alpha, they give you that the alpha is 0.03, that means 0.05 of p-value is more than alpha. So if p-value is more than alpha, then we consider that there is no significant difference in the group mean. So the data does not provide statistical evidence that alternative hypothesis is true. Okay. If the p-value is less than the alpha, then like alpha is 0.03 and p-value is 0.01, then there is a significant difference in at least one group mean. So data provide statistical evidence that alternative hypothesis is true. Okay. So say you have a chart, right? You have a chart like this, and it gives you all of these things. First thing you're going to do is you look at the labels, right? So fully adjusted models, NAT2 status, exposure, fecundability, odds ratio, and 95% confidence interval. And then you look at these ones, so NAT2 and caffeine, NAT2 and alcohol, NAT2 and smoking, right? So then usually this is given with a lot of literature, but I'm just fast forwarding to the chart. So I'm just going over it, not that this is what's asked. Okay. So NAT2, you can see that there is a status that says rapid, slow, rapid, slow, rapid, slow. And then we get odds ratio, which is 0.96 or 0.81. Right. So less than 1, that means it reduces it, right? More than 1, it increases it, reduces it, increases it, reduces it. So overall, we see a pattern that in rapid, it's higher, and slower, it's lower, right, compared to the rapid one for all of them. And then we look at the confidence interval. 0.50 to 1.85, right? So confidence interval, when we are dealing with OR and RR, if it includes 1, that means that it includes the null hypothesis. Okay, so what is the null hypothesis? If it includes 1, that means like I said here, if it's less than 1, it reduces it, right? And if it's more than 1, it increases the effect. Okay, that means there has to be a point where everything is equalized. That means there is no increase or decrease in effect, and that's at number 1, right? So when you have 1, that means there is no significant difference, or there is no increase, or there is no decrease in effect. So in effect, as in um, the caffeine being exposed to NAT2, whatever it does, that difference basically. So if the confidence intervals includes the number 1 in it, that means it's not significant finding. So we do not consider that study to be good enough for us to take any action on it. Okay. So here 0.50 to 1.85, it includes the number 1, so this is null. So we don't look at this. 0.67 and this is also null. This is also null. This does not include 1. Okay. This does not include 1. I mean, this it does include 1, and this does not. So the only ones that are significant finding here is NAT2 and smoking, slow, and NAT2 and alcohol, slow. Okay. So here the question is, what type of study was this, right? So it was basically, this feels like it's stratified. So this is confounding type of study where NAT2 is the effect modifier. So when NAT2 is added to caffeine, it increases its effect on it, basically. Okay, in the smokers. Okay. The main thing was that you figure out that NAT2 is the effect modifier. I just went over the whole confidence interval thing with you. Okay, so this diagram, if you understand how to use this, it's going to help you in all of the questions where any of these tests are involved. So dependent variable and independent variable, what are these? Independent variables are going to be the ones that the researchers are trying to use to build their study based on. Okay, and dependent variables are the findings that they are going to do in those studies. Okay, so independent variable can be any qualitative type. Qualitative would be a categorical, so men, women, or it could be people with cholesterol less than 100, between 100 and 300, and more than 300, right? Okay, or that could be quantitative actually, sorry. This would be obese, non-obese, or something like that. If you have an example, it's quite easy to figure out what it is. Okay, but the number ones, it's going to be quantitative. Okay. Again, dependent, same thing, categorical and quantitative. I go over it in the video. Right now, I'm drawing a blank with examples. Okay. So qualitative and qualitative. So if independent variable, so if you have a chart, and so say you have a table, so the top ones are usually going to be the independent variables, and the side ones are going to be the dependent ones. Okay. So if you have qualitative and qualitative, it's going to be chi-squared. Okay, so that was this one right here. Okay, so telemonitoring and usual care. So how many patients were there, right, for telemonitoring and for usual care? And then primary endpoint, death or readmission. Okay, so this many people and these many people. So this is all like chi-squared. So this was qualitative, this was qualitative. Okay, chi-squared. Another one is logistic regression. Okay. Then if you have qualitative and then quantitative in the dependent variables where you're keeping track of blood pressure or heart rate or stuff like that, right? Or cholesterol. That's if it's between two populations, so like a man and women, or people under 30, over 30, or something like that. As long as there are two pools that you're working with, it's going to be t-test. Okay, if it's more than two, then it's going to be ANOVA. And then if there's a line they're talking about where sorry, right, linear regression, that's the one where the dots and then like it's between 1 and -1. If it's -1, then it's going to go downwards, right? And if it's positive, then it goes upwards, the line. That's what the regression one was. Logistic regression, I don't remember that one. Quantitative. I feel like that's the one where if one variable increases, the other one increases as well. If one decreases, the other one decreases as well. Is that one? And then quantitative is correlation and linear regression again with this one. Oh, right, no. Correlation one was the one where one increases, the other increases, or one decreases, other decreases type thing. Okay, so they're related to each other, the variables. So those are the quantitative ones. So now if you just pay attention to this chart, remember it, draw it on your wall or something, and look at it and until like this is burned into your head. It will help you out for those questions. Try to, if you don't get those, try to learn it during the QBank about which one were the independent variable, which one was dependent before submitting. And after you submit it, just make sure that you got them right. If not, then just, learn it there. What is independent and what was dependent. And then eventually you'll get the hang of it. Which of the following is the closest to the probability that an individual will be correctly classified by a test? This formula, I didn't know this one, so I added it. I don't think it was in the first aid from step 1. So if they ask you for the probability that an individual will be correctly classified by a test, it's called accuracy. And this is true positive plus true negative divided by the total of TP, FP, TN, and FN. Okay, grab this from step 1, FA. PPV means if test is positive, so predictive positive value is TP over TP plus FP, right? So it means if test is positive, there's still 75% chance that the patient does not have the condition. Okay. So since positive predictive value is 25%, that means there's still 75% chance that the patient does not have the condition. Okay. That's basically what it means, because it's true positive divided by the summation of TP plus FP. Okay. Negative predictive value means if the test is negative, okay, there is still 4% chance that the patient has the condition, right? So negative predictive value is 95%. Okay. So if the test is negative, there's 95% chance that it is negative. However, there's still 4% left over. That means that they still have the condition. They could still be positive for the condition. It just didn't get picked up. Okay. So negative predictive value is the probability that an individual does not have a disease given a negative test result. It is calculated as NPV equals that. Negative predictive value, NPV, determines the likelihood that a patient with a negative test result truly does not have the disease. Okay. Some different questions. Okay. Keep that to the side. Sensitivity. Okay, let's bring that back. Indicates how well a test can screen for a disease. Okay, so when you're talking about the predictor values, it's not about the test. Okay, it's more about the prevalence of the condition or the disease. Okay, it's based on that. However, sensitive and specificity, it's based on the test. Okay, so sensitivity indicates how well a test can screen for a disease. A higher sensitivity makes it less likely that there are false negative, right? So if there's a high sensitivity, the top number is going to be about the TP. So the higher the TP, the less chances of FN making a dent in this result, right? So it indicates how well a test can screen for a disease. A higher sensitivity makes it less likely that there are false negatives, meaning that a negative test better rules out the disease. Okay, so SNOUT was the mnemonic for that. Sensitive test that's negative rules out the disease. Okay. And specificity indicates how well a test can confirm the diagnosis. The higher the specificity, the less likely there are false positive. Okay, meaning that a positive test result better rules in the condition. Okay, so if there's high number of true negatives, okay, that means if you get a positive in this test that has a high specificity, that means it rules in the disease. And if you're getting confused by all of these, just go back to the example of um, SLE, right? So SLE or rheumatoid arthritis, ANA, is a sensitive test, but it's not specific. So it will give you 96% sensitivity and it will rule right. So 96%. If it's positive, then you know that ANA is positive, but you don't know which disease it is. So to figure out which condition it is, we do a specific test, right? We do for rheumatoid arthritis. It was what was it? The cyclic one, CCP, right? Citrullonated peptide one, or whatever. Antiphospholipid, right? I'm trying to think at 3 in the morning, but what was the other ones? The anticentromere for scleroderma and all of these, because they all give positive ANAs, right? Scleroderma, SCL, 70, anticentromere, antimitochondrial, whatever, or topoisomerase. Not sure if that one gives ANA too, but anyways, you get the gist of it. So ANA, we use sensitivity to figure out if there is a condition that is related to them. If we get that, then we go and zone in into like specific tests, and that's how we rule in the disease, right? So indicate how well a test can confirm the diagnosis. The higher the specificity, the less likely there are false positive, right? So if you do a specific test, chances are there are lower false positive. That means there are better rules in the condition. Okay. With sensitivity indicates how well a test screens for a disease. Okay, so we're screening the test, like ANA is a good test to screen for the disease. A higher sensitivity makes it less likely there are false negatives. Okay, so if there is some condition, we want it to be picked up by the sensitive test. Okay, meaning that a negative test better rules out the disease. SNOUT. Okay, so if ANA is negative, then we can be sure that it's not SLE or scleroderma or anything else like that, such thing, right? Okay. Sensitivity determines the percentage of patients with disease who will have a positive test result. Okay, so sensitivity determines the percentage of patients with disease who will have a positive test result. Specificity determines the percentage of patients with no disease who will have a negative test. Okay. Because just basically go to what the top numerator is, right? The TN is here, so true negative. So it's for specificity. It just talks about patients who don't have the disease and how often they will have the negative test here, who has the disease, and how often they'll have a positive test. These measures describe the performance of diagnostic tests and are not affected by pre-test probability of disease or disease prevalence, right? Those are these things. So don't confuse the two. Okay. In contrast, this patient is asking about the probability of disease given a test result. Okay, so in contrast, this patient is asked about probability of a disease given a test result. Okay, so that's this one, right? So they were given that this is the test result and all that. I feel like that's the one, same question. Anyways, just keep the stuff clear in your head and it should be fine. We have a question where they state that there's 95% specificity. So it means that 95% is true negative and 5% chance of false positive. Meaning that, okay, compared to blood culture, the reference standard for diagnosing a bacterial bloodstream infection and interleukin 27 cut point of more than 5 or more has a sensitivity of 26% and specificity of 95%. Okay. The specificity of the test is the percentage of individuals, that is critically ill pediatric patients, without a condition, for example, bacterial bloodstream infection, who are correctly identified. Okay. That is negative test results by the diagnostic tests. Its complement, that is 100% minus specificity, is the false positive. Okay. Rate. For example, percentage of critically ill pediatric patients without bacterial bloodstream infection who tested positive. The sensitivity of the test, which is 26% of the test, is the percentage of individuals, for example, critically ill pediatric patients with a condition, for example, because remember that's true positive, right? So if sensitivity is 26%, that means there's still 74% chance of it getting less than, not having it, basically. They have it, but it was negative, so false negative, right? Okay. Ooh, I'm trying to zone back in here. Okay. With the condition bacterial bloodstream infection who are correctly identified, that is positive test result by the diagnostic test. Its complement, 100% minus sensitivity, is a false negative rate. For example, percentage of critically ill pediatric patients with a bacterial bloodstream infection who tested negative. The specificity of 95% means that 95% of the critically ill pediatric patients without bacterial bloodstream infection will be correctly identified. That is, test negative, based on the IL-27 cut point of this. Conversely, this means this 5% will be incorrectly identified, false positive. So even though they don't have it, they'll be categorized as having it, right? Okay. In a study with drug X, include the data where participants died since it could be due to exposure to drug X. In a study with drug X, okay. Include the data where participants died since it could be. Oh, okay. So it's basically a study where they're doing they're looking to research drug X, right? And to, I think it was a question about intention to treat or per protocol, right? So in intention to treat, you should include all the participants, even if they died, since it could be due to exposure to the drug X, right? So say they're researching the drug and the adverse effects were like nausea, diarrhea, or something, but they didn't include the participants who died of cardiac arrest or something, right? Because it could be that they didn't figure out that the drug could be causing this stuff, right? So they're like, uh, since the patients were already in the hospital, in their that were participating in the study, they already had some other condition that, you know, led them to cardiac arrest or death. So they didn't include that in the data. But they failed to acknowledge that all of the conditions that led to mortality could be because of the exposure to drug X, right? So if you're doing intention to treat, do this. Or even if like you're submitting the study and where you're saying that there were people who died, you should, add that in the study. So that is something of concern when you're doing a study. So even if it's not intention to treat, you still that is still a thing of concern, right? So include the data where participants died, since it could be due to exposure to drug X. Okay. Factors affecting power. You already know these. Sample size affects it. Variability of the outcome. You don't know this one because this wasn't given in step 1. Effect size, increases the power, and significance level, or the alpha. Okay. These 3 were given in step 1 anyways. So if sample size decreases, power decreases. If sample size increases, power increases, right? So if decreases, more difficult to detect effects. If it increases, then it's easier to detect effects. Variability of the outcome. If the variability is increased, the power decreases. It is more difficult to detect effects. If there's decrease, then there's increase in power, then easier to detect effects. Effect size. If the effect size is decreased, power is decreased of the study. More difficult to identify small effects, right? And if its effect size is increased, then power is increased because it's easier to identify large effects. Significance level, or alpha, right? If it's decreased, again, power is going to be decreased. Stringent threshold for statistical significance. If the factor of significance alpha level is increased, then power is increased. Lenient threshold for statistical significance. So power describes a study's ability to detect an effect, for example, difference between groups, when one truly exists. Power is influenced by 4 factors as follows: increase in sample size increases power, decrease in outcome variability increases power, increase in effect size increases power, and increase in significance levels increases power. Okay. Water break. Okay, so temporality of different study design. Again, you've seen this in step 1 QBanks as well. Okay. How do I approach this? Okay, let's read this first. A cohort study begins by identifying individuals as exposed or non-exposed to a single risk factor, and ends by comparing the incidence of one or more outcomes, that is disease, between the 2 groups. In a cohort study, participants are initially identified based on their exposure status and then followed over time to assess development of the outcome. Okay. So there are 2 types of cohort studies. There's prospective and there's retrospective. Okay. So in present, they look at the risk factors. So say smoking, right? So you have smoking, people who smoke and people who don't smoke, and then you follow them in a particular population, like say in Beijing or Delhi, right? And then you compare the disease incidence, and over time, after 5 years, you compare how many people in the cohort got some kind of lung disease and how many didn't, right? So that's risk factor. Okay, so identify, basically, if you can tell the difference between risk factor and disease, I think it's easy to figure out which type of study it is. Okay. In retrospective, what they do is they say they want to figure out in this population if people are going to if people were exposed to this, what happened, right? If they got the disease or not, right? They're going to compare it. But again, they're gonna talk about disease, the risk factors. They're not gonna have a control group. Okay, so they check the data, they go back, and they figure out how many people had high cholesterol and how many people had normal cholesterol, and then they keep going and then see how many people got, um, how many people ended up with myocardial infarction, right? And then they compare the disease incidence. Okay, so that's what that is. Okay, and OO are relative, right? So if they're relatives, then you do relative risk ratio, RR, in these studies. Okay, the most common one that we confuse it with is this case control, right? So case has A and O is different than A, odds ratio, right? So it's at odds with A. That's how I remember it. Anyways, here they will always have control group, okay, and it's gonna be about the disease. So they will have someone who, a control group where they had nobody had cardiac arrest, and then they will have a disease group, disease cases that where people had cardiac arrest, right? And then they go back and see if they were exposed to any kind of risk factor, right, or how often they were uh, exposed to it. Okay, always they'll have control groups, whereas in here you don't have control groups. So if they talk about control group, it's always case control. If they don't talk about it, it's this. There's also a pattern that I picked up on is when you're reading the question stem, the first thing they mention, check if it was a disease that they mentioned or was it the risk factor they mentioned. Okay, if they mention the disease, it's usually going to be about cohort. It's going to be about the case control, and if it's the risk factor that they mentioned first, it's going to be about the retrospective. The cohort, right? So researchers want to figure out if smoking has caused more uh, lung cancer or not, right? Something like that. Or researchers want to see what effects have led to myocardial infarction, right? So if they mention a disease first, it's going to be usually about case control. If they mention risk factor, it's going to be cohort. Okay, that leaves the other ones to figure out. So clinical trial is going to be treatment group and control group, and then you compare the outcome, right? This is not going to be an observational study. Clinical trials are experimental studies, so it's quite easy to figure out, whereas case control and retrospective ones are going to be mostly observational ones. Okay, so clinical trial, it just is different. It's experimental. Cross-sectional, it's just right now what's happening. Okay. Risk factors, they compare in that, and then disease prevalence. So how many people have it so far and what risk factors they had it. It's not going to be retrospective or prospective. It's basically how many people in this year had it. Right. Easy to figure out, I think. What is a confounder? A confounder is an extraneous factor that has properties linking it with both the exposure and the outcome of interest. Okay, I think it goes into more detail down here. If not, I'll just cover it right now. Okay, let's just cover it right now. So say you have so the famous example, coffee, right? So coffee leads to lung cancer or lung disease. Okay, so when they did the study, they found that people who drink coffee were more prone to having lung disease. So they incorrectly stated that coffee leads to lung disease, right? However, they didn't stratify it. And through that, what you find is in a confounding study, you're going to have a confounder, right? Where coffee is related to something that is also related to lung disease, okay? And that is smoking. Okay, so here smoking is the confounder, okay? Or I just say co-founder. Okay, so if smoking, coffee is leading to this, smoking is a co-founder of lung disease as well, right? So what turned out was that people who drink coffee were more prone to smoking as well. And because of smoking, it's going to be related to lung disease. So this is your confounder, right? Smoking is related to coffee. It's related to the outcome as well. However, yeah, so when you have a confounder, it has to be related to the exposure and it has to be related to the outcome. Okay, so smoking is that. Okay, another one was like where smoking is related to causes liver disease, right? Smoking causes cirrhosis of liver or something like that. Okay, however, the confounder is here that people who smoke are also prone to drinking more alcohol. Okay, and alcohol causes liver disease as well. So now here, the exposure was smoking, outcome was liver disease, confounder is alcohol. Okay. So to avoid these, we do, stratified studies and all that to figure out if stating that smoking causes liver disease is true or not. Okay. All right, so absolute risk reduction. The difference in risk attributed to the intervention as compared to the group. If 8% of the people who received a placebo vaccine developed the flu, and 2% of who receive a flu vaccine versus 2%, right? So 8 minus 2, 6%, or 0.06 is your absolute risk reduction. That is your C, right? So this is going to be control one, right? So not exposed to the treatment or whatever. So C and D, so that's going to be C over C plus D. So that's your control group minus this, right? A over A plus B, right? That's your exposed group. So similar to that, if you want to look at a relative risk, again, that's treatment group divided by control group, right? So treatment group over control group. It's, what was that? Hold on. No, here. Okay. Relative risk control. Okay, that's where I'm looking. Whoops. Okay. No, this is different than the old one. That's why I'm getting confused here. Okay. So ARC is the control group and ARI is the ARI and ERT. I haven't seen this formula before, so that's why I'm getting confused. But intervention groups, right? So control group minus the treatment group, right? And that is similar to ARR. So, right? So ARR, where'd it go? Right here. So control group minus the treatment group. Okay. I'm back on track now. Okay, so that was ARR, right? So that's similar to this. So ARR over control group, we can plug that in here as well, right? So right here, ARR over control group. Okay, so that's that. So relative risk reduction, if 2% of patients who receive a flu shot develop the flu, while 8% unvaccinated patients develop the flu, then RR equals 2 over 8, which is 0.25. So relative risk reduction was 0.75 or 75%. Okay, so risk ratio was 2/8, and then you do 1 minus that, and then you get that, right? So 1 minus RR, that was the old formula, right? 1 minus RR divided by RR times 100, and then this is the new one. The control minus treatment divided by control, or ARR, which is also control minus that treatment group, right? Divided by that. Cool. Moving on. Spent too much time on that. Relative risk ratio of the probability of an event occurring in the treatment group compared to the control group. RR equals treatment rate divided by control rate, right? That's the same as this. A over A plus B, that's the treatment one, that's the exposed one, or exposure of the intervention, right? Divided by control group. So treatment rate divided by the control rate. Number needed to treat. Okay, so number needed to treat, right? Before that, let's do number needed to harm. Number needed to harm is 1 over AR. AR from harm, right? HARM or HARM. It's given over there as well. So if you remember that, then you should be able to remember that number needed to treat is 1 over ARR. Okay, so absolute risk reduction. So after you do control minus treatment, then you do 1 over that, and it gives you the number needed to treat. This is the number of individuals who need to be treated to prevent a negative outcome in one patient. Okay, so number of patients who need to be treated for one patient to benefit. Okay, so lower the number, the better. If 50 people need to be treated for one person to come out as a positive result, compared that to 2 people who need to be treated and one person to have a positive outcome, that's better, right? So 50% success rate there. Okay. Attributable risk. This is the if risk of lung cancer in patient who smoke is 21% and risk of in people who don't smoke is 1%, then the attributable risk is 21 minus 1, right? So exposed group, right? So exposed group is A over A plus B minus the control group, which is 1%, right? So that's AR. And then there's also AR percentage that you can do, which is risk reduction, right? So relative risk. Relative risk here is exposed group over control, which is 21 divided by 1, right? So that is still 21 minus 1 divided by 21, right? Right, so 19 over 21, how much is that? Let me do it. See if I did it right. Okay, so got the calculator. Okay, so what am I doing here? I lost myself here. Okay, so treatment group divided by control group, so 21 divided by 1 is 21, minus 1 is 20, 20 over that is 95%, so 20 divided by 21 is 95% times 100 is giving me 95%. Okay. I have no idea what that was. But anyways, since we're dealing with percentage here, I can't just plug those in. We need to put it back into, do that. Whereas 21% got, I would put 21. If there were 100 people, then 21 would go here. True positive for the disease. That means true negative is whatever, 79. That would go over here, right? And then 1% who didn't smoke, got the disease, so 1% would go here, right? And then we would do the whole thing to figure out what the RR was. Okay, but so that's why it didn't work out here. Anyways, next, going on to this. Types of studies in the health sciences. Okay, so experimental, randomized, controlled trial, random allocation into treatment and placebo groups, can determine efficacy of the intervention, non-randomized design, non-random allocation into the treatment and placebo groups, can determine efficacy of the intervention. Observational are the cohort, cross-sectional, case control, and case. Okay, review is meta-analysis. Okay, so now we're talking about the confounding biases. Okay, here we go. Common type of systemic errors. Systemic errors in statistical studies. Okay, selection bias and observational bias. So selection biases are ascertain sampling bias. Okay, so inappropriate selection or poor attention of study subjects. Ascertainment sampling bias, which is study population differs from the target population due to non-random selection methods. Non-response bias, which is higher non-response rate to surveys, questionnaires, can cause errors if non-responders differ in some way from responders. Bergson bias is the bedside bias, right? So disease studied using only hospital-based patients may lead to results not applicable to the target population. Prevalence or Neyman bias, which is exposures that happened long before disease assessment, can cause study to miss diseased patients that die early or recover. Okay. And then there is attrition bias, which is significant loss of study. Participants may cause bias if those lost to follow-up differ significantly from remaining subjects. Observational biases. Inaccurate measurement or classification of disease, exposure, or other variables. So recall bias, common in retrospective studies. Subjects with negative outcomes are more likely to report certain exposure than control subjects. Observer bias, observers misclassify data due to individual differences in interpretation or preconceived expectations regarding study. Reporting bias. Subjects over and under report exposure history due to perceived social stigmatization. Surveillance detection bias, which is risk factor include factors itself causes increased monitoring in exposed group relative to unexposed group, which increases probability of identifying a disease. So reporting bias, for example, would be if people are their kids who are doing study and they went to a fair and then they're asking people if how many people do they consider in their family to be obese, right? And then they did the same thing by sending it in mail to the surrounding neighborhood, and then they got the results back. And then when they compared it, they figured out that in at the fair they got reported that uh, one in four households were obese, and uh, drinking soda did not, was not significantly related to obesity. And then when they got the mail, they got that 3 and 4 were affected by the soda and considered as obese, right? So either was underreported or overreported depending on that. So that would be reporting bias. Uh, so what is confounding bias? Confounding bias may lead to false conclusion about the association. That is statistically significant association that are truly invalid. Okay. IRB consent, for people who aren't aware of this, it is a review board that you need permission to do, use the data basically. Okay, and at a research facility or any type of research thing you're doing. I don't know where either, but I know that the Mayo Clinic does it, Cleveland does it, and hospitals do it. So if you're doing it on your own, you don't need to do that. You do need consent though. All research projects involving human participants must be submitted to an institutional review board, IRB, for review and approval before study initiation. Research studies that use only secondary data, that is, medical charts, and that involve no more than minimal risk to participants do not require informed consent. Okay, so if you're using only secondary data and that does not involve that involves no more than minimal risk to the participants, it does not require informed consent. Okay. Methods to control confounding. So design stage. You can do matching, restriction, and randomization. Analysis stage, you can do stratified analysis and statistical modeling. Randomization is used to control for confounders during the design stage of a study. It helps to control for known, unknown, and difficult to measure confounders. Okay. For rare disease, okay, this is important. For rare diseases, the odds ratio approximates the relative risk ratio. Okay. So if scientists did a study and they found the OR, and they say that this can be used as to approximate the relative risk ratio. Why is that? It's because it is in a rare study and a rare disease. So in rare disease, OR can approximate RR. Okay, again, in rare disease, odds ratio can approximate relative risk. Okay, matching study participants with their neighbor for control is to prevent confounding bias. That goes back to this, right? So matching studies participants with their, let's just move that over there. Per protocol versus intention to treat analysis. You can just check out the diagram there. Okay. Per protocol analysis includes all those participants who strictly adhered to and completed the study protocol. That is non-dropouts. Okay, so per protocol. So randomization, we have treatment A where people, 3 people were present and then 5 people were dropped out. Whereas in treatment B, there were 4 people who were present and 3 people who were dropped out. So when you're doing per protocol analysis, you're only going to consider 3 out of 8 people, and for B, you're only going to take 4 out of 7 people. Okay. 2 dropped out in A, and 3 dropped out in in B. So 3 out of 8 people and then 4 out of 7 people, whereas you do not take into account that 3 people dropped out here and 2 people dropped out from group A. Whereas in intention to treat, you take all of those in account and then 3 out of 10 you get, and then 4 out of 10 for intention to treat, right? So this approach tends to provide an estimate of the true effect of an intervention for a perfect scenario, but it can overestimate the effect of the intervention in a practical clinical setting. Okay, when you're doing per protocol, it can provide an estimate of true effect of the intervention. Okay, however, for a perfect scenario, however, it can overestimate the effect of the intervention in a practical clinical setting. Okay. Okay, so a confidence interval always contains the sample value at the center of interval. A confidence interval that excludes a null value, that is difference in percentage, does not equal to 0, is statistically significant. Okay, so they're talking about there's no odds ratio or relative risk, right? So we do not consider the null value to be 1 anymore. Okay, we're doing confidence intervals, so we're dealing with percentages, not ratios. When we are dealing with percentages, we do not want the difference to equal to 0. Okay, so what does that mean? So let's go over this. Hospital A, B, and p-value, percentage of adverse effect, and percentage of adverse effect negligence. Okay, which of the following most likely represents 95% interval for the difference in the overall percentage of AEs between hospital A and hospital B? Okay, so we have hospital A, hospital B, p-value, right? So p-value here is 0.003, which is significant, but this is not, so we do not care about that. They are asking about 95% interval for the difference in the overall percentage of AE between hospital A and B, right? They are telling you what to do here. If you comprehend it, what they mean is the difference between the overall percentage of AEs, so this one, between hospital A and B. So difference between this is 3.6 minus 5.1. That's it. That's all you have to do. Okay, and this is the significant. We do not care about this, so we can cross that out. Okay, and the difference should not equal to 0 for it to be statistically significant. And we know that it is because p-value is less than 0.05. Okay, so all we have to do is we gotta pick one of these where it includes the difference and does not include the null value, okay, which is 0 in its confidence interval. So minus 4.5 to minus 0.3. Okay, so we gotta, let me just figure out what the interval is. We're doing 3.6 minus 5.1, which equals minus 1.5. So we want minus 1.5 to be in here. Okay, minus 1.5, right in the middle. We want it to be in the middle, right? So this is there, this is there. Yes, there's no 0, there's no 0. There is 0 included in this, so we can cross that out. There's 0 included here, we can cross that out. We can cross this out. So first 3. Now we are dealing with first 3. Now the difference is a negative 1.5. This one does not include this interval from 0.7 to 0.6, does not include 1.5, so we can cross that out. Now we have 2 left, minus 4.5 to 0.3 and 2.5 to 0.5, right? We want it to be a number that is in the middle for it to be a mean, right? For the confidence interval, because 95% confidence interval is over a Gaussian curve, right? And the Gaussian curve has a mean in the middle, mode in the middle, and median in the middle as well, right? So that would make sense for this one, that we place 1.5 here, okay, 1.5 here, and minus 1 this way will give you 0.5, plus 1 this way will give you, sorry, minus 1 will give you 2.5, and plus 1 will give you 0.5, so it's right in the center. Whereas here, negative 1.5 plus 1 won't give you 0.3, and minus 1 won't give you 4.5, so this doesn't work. So that's why we picked this as the answer. Cool. Next, confounding versus effect modification. Hopefully this is all clear now, but I'll go over this now. Confounding crude analysis, alcohol use leads to bladder cancer. Okay, and there's a significant association. RR is 1.81. That means it's more than 1. That means the effect is increased. 95% confidence interval is giving you 1.06 to 3.10. Okay, it covers the risk ratio in there, so it's significant. However, when we stratify it by smokers, alcohol use, and bladder cancer, there is no association. Okay, RR is equal to 0.95. Okay, confidence interval includes the number 1 now. That's why it's not considered significant anymore. So there is no association. In non-smokers, alcohol does not cause bladder cancer. Again, RR is increased. However, confidence interval includes the number 1, right? 0.34 to 3.13. Okay, so that's how you stratify it. And turns out that there's no association between alcohol and bladder cancer. Okay, so what is the effect modification here? It would be crude analysis, use of oral contraceptive. There's a significant association with breast cancer, stratified by family history. Family history was done. Use of oral contraceptive was a strong association with breast cancer. Okay, because there's family history. And there's no 1 included here. RR is 3.3, so it's significantly increased, 3 times increased, in fact. For people who use oral contraceptive but don't have family history and still get breast cancer, the risk the risk ratio is 1.27, so it's only increased by 0.27 times, right? And the confidence interval does not include 1, but it's very close. Okay, so that's how you do that. Effect modification here was family history. A major disadvantage of the cross-sectional study design is that it is biased in favor of longer lasting and milder conditions. Okay. More severe acute conditions tend to be rapidly fatal and are therefore less likely to be found in a snapshot of the population. This means that a cross-sectional study may not be able to estimate the prevalence of severe acute conditions. This phenomenon is known as late look or Neyman bias. Okay. So like, for example, if a doctor wants to figure out what are the most common conditions found in a old age home, they're going to find things like Alzheimer's, kidney disease, and all those chronic ones. However, they won't find the conditions that are short term, rapid, that have rapid fatality. Basically, I don't know. You get it. That's what that is. I'm just gonna move on. Raising the cutoff point, for example, increasing the inclusion criteria of a screening test results in an increase in specificity and someone's mowing their lawn in the middle of the night. What? What? That's crazy. Okay. Raising the cutoff point, for example, increasing the inclusion criteria of a screening test results in an increase in specificity and decrease in sensitivity. Okay, I got thrown off by this guy who was mowing his lawn outside, and it's in the middle of the night. Okay, sorry. I gotta read that again. Texas is wild, man. Texas is not for beginners. Raising the cutoff point, for example, increasing the inclusion criteria of a screening test results in an increase in specificity and decrease in sensitivity. Raising the cutoff point, for example, inclusion criteria of a screening test results in increasing. Oh, okay. They're talking about this. At what cutoff value that, for example, enzyme level, will the number of false negative be the highest? So if you remember this diagram, right, you go alphabetically N, then P, and then you keep the last names N and P, and then FF here. Right, we only concern ourselves with these. Okay, so they're asking, well, at what cutoff value the that is enzyme level, will the number of false negatives be the highest? So false negative will be the highest when this line moves from B to C, right? So from here to here, so E. And that's basically it, what that is. Okay, and this is saying that cutoff value increasing the criteria, so going from B to C. What does it do? A screening test results in an increase in specificity and decrease in sensitivity. So if you're going from B to C, you're smashing FP. If you smash FP, FP goes down. If FP goes down, then you remember the formulas, right? For specificity, it was Tn over Tn plus FP. So Tn goes up, specificity goes up. Fn goes up. That means TP is going to go down. If TP goes down, sensitivity goes down, right? And okay, that's it, basically. Nothing to add there. Type 1 alpha and type 2 beta errors, right? So again, plus minus plus minus. Plus is there is a true difference, right? So that means HO is, or null hypothesis is false because there's true difference here. This is here, and then our test that we do, so this is the reality, this is the test, right? So true status here is that there is a true difference, and here when we do the test, they say yep, there is difference. So we reject null hypothesis that there's no difference and correctly conclude there is a difference. Cool. However, in reality, if there is no difference and null hypothesis is true that there is no significant difference, however, when we do the test, like the confounding one over here, where we concluded that alcohol use is related to bladder cancer, however, in reality it is not, that means we rejected null excuse me rejected, and bless me, rejected null hypothesis. However, in reality there is no difference. So this is called the type 1 alpha error, falsely conclude there is a difference. Okay, and then there's another instance where there is a true difference, however the study does not find it, and it says that difference calculated as not statistically different, so we fail to reject null hypothesis. Okay, so that is type 2 beta error, and it falsely concludes there is no difference, and if there is no difference in reality and the study also, then correctly conclude there is no difference. So how do we improve this? We improve with all those things that increases beta, right? When beta power or whatever increases, that means the other stuff decreases. Type 2 beta error decreases. Okay. Basic criterion to establish causality, analogy, similar association known. Biological gradient is dose-dependent relationship between cause and effect. Biological plausibility, probable, given established knowledge. Coherence is association should not conflict with known facts. Consistency is commonly, this was like the Bradford Hill criteria or whatever, right? Similar to that. Consistency, cause widely associated with effect. Experimental evidence, effect evidenced by experimental designs. Specificity, cause uniquely associated with effect. Strength of association, cause associated with a substantiative effect. Temporality, causes precedes effect. Okay. Which of the following approximates the relative probability of potential adverse effects in the pediatric institution compared to the adult institution? Okay, so when they ask you about this, when comparing relative risk of two same outcomes in two cohorts, relative risk is equal to rate of outcome in cohort 1 divided by rate of outcome in cohort 2. Okay, so whichever one they're asking for will go on top first. Okay, so when they're asking about relative probability of potential ADEs in the pediatric institution. Here we're talking about ratio, right? Up there we were talking about percentages. Here we're talking about ratio, so this is risk, relative risk, and they're asking about pediatric first, so that will go on top, compared to adult institution, so that will go at the bottom. Okay. This is the line graph. You need to know, if you don't remember, it's the one where they give you sensitivity, 1 minus specificity. So if you want the one closest to the top right corner, B, right? However, the line needs to be touching there. So B wouldn't count, so C would be the closest one to top right corner out of the other ones. So that would be the answer here, if that's what they wanted. But E question mark, okay. What was the question? Oh, okay. So in the ROC graph shown, the cut point E has, okay. Okay. So they're not asking, that wasn't the question. The question was E. So what does E represent, right? So it represents 0 sensitivity and 1 minus 1, so 0 specificity. If you have 0 specificity, what does that mean? You have all false positives, right? So 0 sensitivity and 0 this, so all false positive, and all positive tests results are false positive. Okay, yes. All positive tests are true positive? No. Because all test results are negative? No, all test results are positive. No, because even sensitivity is 0, so maybe this one. Let's see. For a test that is 0% negative, sensitive and 0% specific, all positive test results are false positive. All positive, yeah, so it's this one. All positive test results are false positive, okay. In ROC graph, what was that ROC? Area under curve. Okay, I remember the full form of that. The cut point E has a rate of true positive, that is sensitivity of 0.0. It lies on the x-axis. Okay. A rate of false positive lies on the x-axis. Right, so because 0, it's talking about 0 lying on the x-axis. A rate of false positive, that is 1 minus specificity of 1 or 100%. Right, okay. I hope you followed along to what I was saying. I don't think I messed up, so just rewind back and listen to it again. A parallel study randomizes one treatment to one group. Okay, this is just explaining what a parallel study is. So a parallel study randomizes one treatment to one group and a different treatment to the other group, such as treatment drug to one group versus placebo to the other group. There are usually no other variables measured, such as the 2 blood pressure goals in this study. Okay, we don't have the study, so. What is cluster analysis? Cluster analysis, the grouping of different data points into similar categories, which is not employed in this study. Cluster analysis usually involves randomization of the level of groups rather than at the level of individuals. Okay. Here we have this. This is called the factorial design. Studies involve randomization to different interventions with additional study of 2 or more variables. Okay, so patient randomized to beta blockers, ACE inhibitors, and calcium channel blockers. And then again, within those group, they were further divided into higher blood pressure goal and lower blood pressure goal for each of them. So these are factorial designs. Okay. Baseline patient characteristics help determine the success of randomization process. Okay. Baseline patient characteristics help determine the success of randomization process. Okay. In clinical trials, randomization is said to be successful when a similarity of baseline characteristics of the patients in the treatment and placebo groups is seen. Okay. I feel like that's a similar point to what the confounding one was making. Right. Did I miss out? Right here. Randomization is used to control for confounders during the design state. It helps control for known, unknown, and difficult to measure, matching study participants with their neighbors. For control is to prevent confounding bias. Okay, so success of confounding bias in clinical trials is to be successful when a similarity of baseline characteristics of patients in treatment and placebo group is seen. Absolute difference. So what does absolute difference mean? It means that the treatment group minus control group difference. Okay, so this is the exposed group minus the control group. Okay. And that is also the formula for attributable risk. Okay. In ecological studies, the unit of observation is the population. The unit of observation is the population. Disease rates and exposures are measured in each of the series of populations, and their association is determined. Therefore, results about associations at the population level may not translate to the subject level. If the option says individual in an ecological study, don't pick that as answer. This phenomenon is known as ecological fallacy. The fallacy assumes that the individuals of a population all have the average characteristics of the population as whole. But any association observed between variables at the population level does not necessarily mean that the same association exists for any individual selected from the population. For example, a subject living in an environment with a high percentage of green spaces may not have a lower risk of depression-associated mortality. Okay. A cross-sectional study is an observational study that is used to estimate prevalence of a disease, but it may also be used to examine associations between risk factors and disease in a well-defined population at one particular time. Okay. So internal validity and external validity. Okay, so what are these? The characteristics for internal validity is that it describes causality. That is, if changes in independent variables causes change in dependent variable. Internal validity increases as study becomes more tightly controlled. It decreases as study becomes more like the real world. Okay, so that decreases the internal validity. So what are the threats to the validity? Biases due to confounding, history, maturation, measurement, regression towards the mean, okay, repeated testing and selection. What is the external validity? This is basically describes generalizability. That is, if observed relationship applies to situations or people outside study. The external validity decreases as study becomes more tightly controlled. Okay, and it increases as study becomes more like the real world. Okay. Biases due to artificial research environment, measurement effects, and non-representative sample. Okay. So basically, if they took a, I don't know, just go ask ChatGPT to explain it to you if you don't get it. It's going to be easier. I'll just probably end up confusing you. Precision is the measure of random error. The tighter the confidence interval, the more precise the result. Increasing the sample size increases precision. Okay, so precision is the measure of random error. The tighter the confidence interval, the more precise the result. Increasing the sample size increases precision. Okay, all right. The odds ratio is a measure of association in case control studies to compare the odds of exposure in cases relative to controls. The odds ratio is not a direct measure of risk. Understand the interpretation of an odds ratio of 4.0 in a case control study, recognizing that it signifies a four-fold increase in odds. Okay, if it's more than 1 and your odds ratio is 4, then it's 4 times. If it's 3, it's 3 times. 1, it's null, right? Increases in odds but does not uh, directly translate to a four-fold increase in risk. Okay, so it increases the odds of having it but not the risk. Okay, so there's a difference. Appreciate the importance of distinguishing between odds and probabilities when assessing associations in epidemiological research. Okay, if this doesn't help, let's try to put it in the terms that would help, right? So when they give you four-fold odds, that means that we have disease cases and non-disease cases, right? If someone has myocardial infarction and we have people who don't have that myocardial infarction, uh, between the two, there will be 4 times the odds of having high cholesterol in this cohort compared to this cohort. Okay, that's how you do it. Whereas over here, 4 times the risk increases um, when you compare it over here, right? So if we have people with high cholesterol and people without high cholesterol, and then we compare it, and then they will have 4 times increased amount of risk that they will have myocardial infarction in future, right? Or here, I mean perspective, or they had it, right? Or they will have it, sort of like that. Hopefully that helps. So the difference between 4.0 and case control, it's not that it signifies increase in risk, but it increases the odds, basically, of the risk. Okay. Multivariate OR means they adjusted for co-founders. Okay. So when you have a diagram of all the charts and results and outcomes, and there's one where they say bivariant, and there's one that says multivariant of OR, that means they have adjusted for the co-founders. So use these data over the bivariate ones. Okay. To answer the questions. The p-value in the probability of obtaining a result by chance alone when a null hypothesis is assumed to be true. Its magnitude is compared to a predetermined significance level alpha, usually set at 5% to 1%. To determine statistical significance, a p-value less than the significance level alpha indicates that results will occur by chance less than alpha percent when null hypothesis is assumed to be true. P-value less than the significance level alpha indicates that it will occur by chance less than alpha percentage when null hypothesis is true. Yes. Okay. So normally they do not state, they do not give you the alpha percentage, so we just assume 0.05, right? Because that's where normally it's placed in studies. Okay. A p-value less than alpha is significant, indicates results are p-value less than alpha. Yep. P-value less than 0.01 indicates results are inconsistent with null hypothesis. That is statistically significant association at that significance level. If it's more than alpha, we already went over this, it's not significant. Okay. Hopefully all of that makes sense, because it does in my head. Okay, risk is the following. Sorry, what am I reading? Risk is the probability of developing a disease over a certain period of time. To calculate the risk, divide the number of exposed subjects with the disease by the total number of exposed subjects, that is all subjects at risk. Okay, this is basically just the formula for risk, right? It's asking you to do the exposed divided by the control, or this is, in this case, that they're asking for everyone that's at risk, right? So people who do not have who have not been exposed yet. It's just them wording it differently. It's most of the time this is just about comprehension. And so this is different from risk ratio. Well, I'm wrong then. What is it? Let's see. To calculate the risk and divide the number of exposed subjects with the disease by the total number of exposed subjects, that is all patients. Okay. It sounds the same, but it's different from risk ratio. So if we have 10 people with tuberculosis out of 20, that means there are also 10. Well, let's say 30. Right, so to calculate the risk, divided the number of exposed subjects with the disease, so TB, so that's 10, by the total number of exposed subjects, that is all patients at risk. So that's 20, so 10 over 20 then, 1 over 2. So risk is the probability of developing a disease over a certain period of time. Oh, okay. Okay, so risk is the probability of developing a disease over a certain period of time. This is different from the risk ratio. Okay, so when you're doing the calculation and all, what you will do is you take, to calculate the risk, you divide the number of exposed subjects with the disease by the total number of exposed subjects. Okay, so people who haven't had it. It still sounds like risk ratio to me, but I wrote that it's different from that, so it probably didn't work out that way for me during the questions. Anyways, spend enough time on that. Hopefully, you'll remember that. Prevalence and PPV and PV. Prevalence increases PPV, decreases NPV. Prevalence decreases, then that increases NPV, but it decreases PPV. Okay. As disease prevalence increases, the positive predictive value increases and negative predictive value decreases, and vice versa. Okay, unadjusted and adjusted OR for association of AGD, tertiles, and presence of endometriosis. Okay, this. How do we read it? We have OR on this side. Okay, so OR, we know null hypothesis is at 1. Excuse me. Right, and we have 3 tertiles. As the tertials go, the distance between the AGD ones, it decreases, right? AGD distance from posterior foreshead to the upper verge of the anus. So they're trying to prove that the shorter the distance, the more chances increases of endometriosis, right? So distance from that to that, and this. Okay, so this is for the unadjusted, this is adjusted squares, by age and BMI, and then triangles are adjusted by age, BMI, vaginal delivery, and episiotomy. Okay. So if they're asking you which one is the significant finding here out of the three, it's going to be tertile 19.7 mm. Why? For 1, tertile 3, it lands on 1, right? So that is not going to count. Tertile 2, here the lines that represent the 95 percentile, right? It includes the odds ratio of 1 in it, right? 95 percentile here, 95 percentile here, and here as well. It includes 1. So this is also not significant then. Here, the lines that represent 95 percentile does not cross 1. So there, we consider that significant. Okay, so that's the significant one. I forget what the question was asking. Oh yeah, which one is significant? There you go. The vertical lines that do not cross OR equals 1. Okay. And then last one. Get rid of these. Crohn's disease activity index, CDAI, more than 150 plus, 100-point increase in score, and the need for anti-inflammatory rescue treatment or primary surgical intervention compared to placebo. Okay, so what I'm saying is be mindful of little asterisks and crosses in the legends, because they will, be important when you're trying to figure out what the answer is. So little asterisks right there and little cross. So cross, when you're talking about like odds ratio, what is it compared to, right? So it's compared to the placebo. Sometimes it makes a difference to know that, okay? When there's multiple variables there. Even the star, Crohn's disease activity, CDI more than 150 plus, 100-point increase in scores. So small little things like that, it matters. Okay, so be mindful of that. And that's it. We're done with the notes and biostat. Good luck. See you in the next one.